I'll let you take over.
Sure. Just a couple more minutes. Oh, I can just do the welcome. Can you all hear me? And I hope you can hear me fine. Great. So, hi everyone. Welcome to the 9th. Roger that. I can't believe we're 9 years old. Very appropriately on Valentine's Day, because this is a true labor of love for us. And so we're so excited to bring this to you. And also appropriately on what would have been Roger's 90th birthday tomorrow. So happy birthday to Roger. Our first guest speaker today is the incomparable Bruce Waggoner from NASA's JPL. He's mission assurance manager there, and he graduated from the University of Nebraska with a BS in Physics and Astronomy. He has worked there for 40 years, so clearly he loves his job, supporting dozens of Earth orbiting and deep space missions. And he's going to talk to us today about communicating appropriately for our conference theme with Voyager 1 from 15 billion, that's billion with a B, miles away. So take it away, Bruce.
All right, good morning. As you heard, I'm the mission assurance manager for Voyager and several other missions. My job is basically to be a risk manager. Sometimes teams make mistakes, and I'm supposed to be a little bit off to the side and make sure people are actually thinking things through all the way, because we all know how team dynamics work. I also manage risk in just a more technical sense as well. So this talk is not work that I did per se. It's work of a huge group of people, the Voyager flight team, which is a pretty small team, the larger anomaly team, and then the Deep Space Network, which is a set of antennas around the Earth that track Voyager and many other spacecraft. And this is the story of how we saved Voyager 1 after a very, very serious flight data computer anomaly that we had back in 2024, or 23 actually, into 24. Just a second here. There we go. All right. So to start, I want to tell you a little bit about the backstory about the interstellar mission and what Voyager's doing and what the status of our spacecraft are. So I think many of you are aware the Voyager's launched in 77. They completed the grand tour of the solar system, visiting all of the 4 outer planets. Jupiter and Saturn had been visited before, and then we have Uranus and Neptune were visited for the first time by Voyager 2. So these encounters changed everything we knew about planetary astronomy. It was incredible how much we learned from them, even in informing us about the terrestrial planets. The Voyager interstellar mission began in 1990, and its goal was to explore the outer heliosphere, which is the magnetic bubble that surrounds the sun, which is enormous, and then actually get into interstellar space and study the boundary region between them. So I actually think that now that we're in interstellar space, this is the most valuable data the project will ever return. And that's because it's going to be very hard for any spacecraft to get where we are today. And we actually have 2 spacecraft there. So I think this is really critical data. We're going to get data from the other planets eventually because they're probably higher priority, but this is unique data. As an example of what it looks like, the bottom panel here, if you can see my cursor, this is Voyager plasma wave spectrometer data. So on the y-axis, you have frequency of the radio waves or plasma waves you're seeing, and across the bottom is time. And we're seeing the time span from when we think we entered the interstellar space area out to the current day. And you can see that initially we did see the influence of the sun here. These are basically solar events that we see echoing out many, many AU from the sun. And you notice there's a thin line trailing along through that bottom plot. That thin line is the electron oscillation frequency. So it tells us the density of the plasma. We have other instruments as well, which we'll talk about, but having this density measurement is absolutely unique. And that's typical of what all the Voyager instruments are giving us today. In the upper right, we have astrospheres. So astrospheres are nothing more than simply heliospheres around other stars. And we've been able to see these for decades, of course, using telescopes. But the point is, the photons are telling you something, but if you don't know the base conditions, it's very hard to interpret what those photons mean. Voyager's giving us one data point we can use to begin to refine those models. And then finally on the bottom is people use quasars to map out the local clouds of dust and gas, and other methods as well. Again, Voyager's giving us that ground truth that allows us to understand the data we're seeing in some of these observations. So Voyager did planetary science, it did heliospheric science, and now we're finally becoming astrophysics mission, which is pretty exciting. Our instruments. We have on the left the magnetometer instrument at the end of a 13-meter boom. We have the plasma wave antennas sticking out there on the bottom left. And the magnetometer does magnetic fields, obviously. The plasma wave spectrometer looks at radio and plasma waves. Plasmas are magnetized gases, essentially. They're ions, and so the magnetic fields cause them to behave differently, and waves can propagate through them. The particle instruments on the right-hand side are the cosmic ray subsystem, low energy charged particle instrument, and the plasma experiment. Plasma experiment is basically off on both spacecraft now, but we're still using it occasionally. It measures thermal plasmas. And this spacecraft is very large. That dish is 3 meters across. So these are not little spacecraft by any stretch of the imagination. So this is a little map to tell you where we've been. The map starts at 20 AU, which is Uranus's orbital radius. So an AU is the distance between the Earth and the Sun, about 8 light minutes. And up on the upper left, you can see the average Earth-Mars distance, which of course the typical distance many of our missions operate at. You can see the Voyagers actually started the Voyager interstellar mission out at 30 to 40 AU. And so they have progressed out past the termination shock, which is where the solar wind goes subsonic into the heliosheath, which is a more benign region, and then crossing what we think was the Heliopause in the 2012 timeframe for Voyager 1 and the 2018 timeframe. And you can see they're currently very far away at 163 AU and 136 AU. The y-axis is the ecliptic latitude. So if you imagine yourself inside one of those clear globes, you can look out and see the latitude lines, right? That's simply the latitude of the heliocentric latitude. So it's the latitude from the sun. So Voyager 1 is going north, Voyager 2 is going south. So our spacecraft status. Voyager 1 is 15.2 billion miles away, or 163 AU. Voyager 2 a little behind. Voyager 1 light time is 22.5 hours. This means that it takes us that long to get a Command 2 Voyager after we send it, and then 45 hours until we can get a response back. So we're coming up on two days in terms of the two-way light time. In terms of speed, they're going very fast still relative to the sun. Those first two speeds are relative to the sun. That's 3.6 AU per year and 3.2 a year for Voyager 2. Now the solar system is moving around the galactic center at 46 AU per year. So the Voyagers are moving slightly faster. They're going out through the nose of the Heliopause, as the diagram in the upper right shows you. And they are going to be distancing themselves from the sun. They're actually gravitationally bound to the galactic center. So the Voyagers will return to their launch point in about 230 million years. All right, so this is a candle, obviously. We all have experience about looking at a candle from close up, putting our hands around it and feeling the heat, right? That's about 80 watts of energy if you go across all wavelengths. So imagine that amount of energy. I want you to divide it by 6. That's actually the energy that our transmitters use. So we can see that from 15.2 billion miles away, which is pretty amazing. The way we do that is we use a 70-meter antenna, this large one here, or we use 3 of these smaller 34-meter antennas. And when you do that, you can actually see 160 bits per second. Really high data rate, right? These spacecraft continuously are broadcasting. Right now, Voyager is visible from Michigan, and you guys are being bathed in a few photons from Voyager 1. But this is, we only track this data when we have antenna passes to actually see the spacecraft. So we broadcast continually, but we only get the data occasionally. We actually can go up to 1.2 kilobits per second, but to do that, we have to array all the antennas. Usually it's 5. This is a cool test we did this year. This is all 6 of the Madrid antennas pointed at Voyager, which is the first time we pulled it off. So it's a pretty cool picture. The reason we go to the higher data rate is that first data I showed you from the plasma wave spectrometer We store that on our fancy 8-track digital tape recorder and play it back. So that gives us that data set that I showed you. We can only uplink from the Canberra station now, and that's just because of a high-power transmitter constraint, and that's at 16 bits per second. So the Voyagers have no safe mode. We have very simple, robust fault protection. Some spacecraft safe themselves. We don't. We keep everything running, and the processors just kind of restart, and we hope for the best. And it actually works really, really well. We have 94 years of experience with our flight systems between the two spacecraft, and our flight team is currently about 12 people, and many of those folks are part-time. Including me, I'm about 1/10 time. So our biggest issue is declining power and thermal margins. So we have 3 RTGs on our spacecraft. They contain plutonium dioxide, and the half-life of that is about 88 years. So we've used up about a half of a half-life. So we're down to, those generators are now about 200 degrees Celsius internally. And the difference between that temperature and the cold of space moves across thermocouples, and that's how we generate the electrons. Our spacecraft require about the same energy as a vacuum cleaner or rice cooker right now, and they're being operated with an unregulated bus. This is something new we've done in the last few years. It's designed to let us get to some power that's that we can reach without using the regulator. So we're doing kind of crazy things to keep things going. And then these margins are always tight. We're always within a year of having to do something like turn off an instrument or try something like unregulating the bus. So this is our biggest problem we have. In terms of our health, this is a functional block diagram. We have our computers in the upper left, telecom at the bottom. Our attitude control computers and parts are in the middle. We have science and tape recorder over here on the right-hand side. Power, which is a big issue for us. We really don't have power to 2040 anymore. This is probably heading more to 2030 based on some recent data we have. And down in propulsion, this is another problem area for us. Our thrusters are aging and clogging. But if you look at this for an almost 50-year-old spacecraft, it's pretty great. The area I want you to pay attention to are the flight data computers here in the upper left, going down to the telemetry modulation system, the TMU, and down to the radio frequency subsystem down here, all of these telecom components. Those are going to be important as we move forward. Voyager 2, same thing. We just don't have many failures. These are great spacecraft. They've been very healthy. We have a lot of degraded systems. Typically, we still have some redundancy in most places. You can see thrusters are, again, an issue. So this is a plot that shows you from 2013 to present day how many actions we've had to take to either delay or avoid mission degradation or loss of spacecraft. You can see that back a decade ago, things were pretty nice, and recently things have been pretty rough for us. And that's just because they're getting older and we're having to operate with thinner and thinner margins. So this is that same small flight team is having to deal with more problems all the time. The last thing I need to bring up to speed before we get into the meat of the talk is talk about our computers. So we have 3 different computer types on the spacecraft, and there are 2 of each type. These were the first reprogrammable deep space flight computers. The computers operate without using microprocessors, and each has its own unique JPL constructed instruction set or assembly language. These are humanity's oldest continuously operating computers. So pretty amazing. And the 2 on the left, these are Viking machines, essentially. They were identical to the Viking computers. Essentially, they're 18-bit word machines, interrupt processors with 4,000 words of plated wire memory, which is a very cool type of memory where you impart a magnetic field on a section of wire and store data there. It actually works really well, and it's very radiation hard, which has been a big boon for us. Compared to most spacecraft, we're very radiation hard. Attitude control subsystem is basically the same computer, except they have an extra assist computer, basically, that kind of helps move data between the 18 and 16-bit bus. So the 2 computers are the same. We use both CCSs. We only use one of the ACSs. The computer on the right is the one we care about, the flight data system. This is a 16-bit word machine. It has modular memories and about 8,000 words of CMOS volatile memory. We only use the A side. This is a very critical computer because it commands the instruments, collects telemetry, formats coax and formats telemetry, and it also provides the timing for the spacecraft in a couple of ways. All right, so this is what people want to hear about, the anomaly in the diagnosis. So things began pretty normally in November 23. We came up on a pass, we saw carrier, but then we couldn't lock up in telemetry, which is very unusual. So after several days of this, the DSN kept looking and making sure it wasn't a ground problem. They determined that we were seeing a stream of 0 and 1 symbols, and there were no telemetry frame markers. These frame markers are basically how you know where you are in telemetry. It's like punctuation on a sentence. You have words coming down, a capital letter or a punctuation mark tells you where a frame marker is, and so you can parse the data. We weren't seeing any hint of those, and a series of 0 and 1 symbols is effectively like a dial tone, just nothing. And so the result of this was the flight team had no visibility into the spacecraft state, except that we could see that we were dead banding. Our signal strength varied slightly. The downlink carrier and subcarrier frequencies were per predict, and we could command the spacecraft, and I'll show you that in a second. So obviously, this is a very grave problem. One of our project scientists compared this to trying to find out where your monitor cursor is with your monitor out. It's fairly difficult to figure that out. So our first steps, well, we obviously thought about the FDS, the flight data system, that flight data computer I showed you, the telemetry modulation unit, or the radio frequency subsystem. So we commanded changes, and that's what you can see in this plot. This is subcarrier frequency changing per command. And generally, we could command the TMU and RFS, but sometimes it didn't work, which was really puzzling. So keep that in the back of your head. So we really were thinking it was the FDS, but somehow there was something else going on which we didn't understand initially. So all of this data that you're going to see from the DSN is using the open loop recorder. And it again showed that the TMU was giving us a clock signal from the FDS. So the clock was at least working. And so we really just, like I said, we had to keep working on the FDS angle. So that was our top priority, was to figure that out. Unfortunately, the person who was the expert had retired a number of years ago, and the backup had also retired. So we were looking at old documentation, in many cases over 50 years old. So it was very hard to find some of it. As you can see, a lot of the information is hand-drawn or handwritten. And then the sources were often contradictory or ambiguous. And of course, that's to be expected on a 50-year mission where you have many updates at the flybys, the planetary flybys, and the beginning of the Voyager interstellar mission, and then all of the subsequent failures. So we actually shouldn't have been too surprised by this, but the FDS was the subsystem we knew the least about. And then we found some interesting things like this page, which is my favorite. This is where someone has circled something as being important and then crossed it out without any sort of notation. So what do you do with this? We didn't know, but this was one of the key things that we wanted to understand. So you can kind of see some of the issues we had. It was even so bad at some point we weren't sure if we should send things to the FDS, most significant bit first or least significant bit first. So what we did was we would do more research, we'd debate it, but ultimately some of our decisions were our best guesses, and fortunately we got it right. So the functional block diagram of the FDS is a little more complicated. I'll go through it just briefly so people understand the depth of the problem. So at the top, we have the memory, of course, where the flight software lives. Memory B is failed. It's potentially useful, but not easily useful. The processor, of course, is running the code and managing all of the data it's supposed to manage. We have a commanded code entry, a state vector box, which basically controls the redundancy. This is the parts that have redundancy. We have an oscillator and timing chain, engineering data tree. We have I/O for the tape recorder, the science instruments, the modulation system. And then we have 2 power subsystems and a backup inverter. So a lot of different pieces here that we could play with. And so what we wanted to do was select the components that were most likely to have failed, and then which ones we felt the most comfortable playing with. And the Venn diagram that contained those 2 features were the things we wanted to try initially, and then things that didn't fall in those categories we'd try later. Because of that long wait time, we kind of fell into a weekly schedule because it took us time to research. So we would observe the results of a test. We design the next test based on research, build the commands, radiate them, wait 2 days, and then observe the results. And this was our repeat strategy. So as you can see, with the box that looks like that, we were essentially playing 20 questions with the spacecraft. So each component switch represented a risk-benefit trade. As I mentioned, we had to go through what were the risks, what are the benefits. Each of these blue boxes is one of those trades. If at any point we had gotten a successful answer, a successful resolution, or a change, we would have gone to the little stop sign and stopped and proceeded with recovering. But as you can see, we kept asking the spacecraft questions and it just kept saying no. So after about 20 of these, we finally had a little success. But what this did do for us was it allowed us to eliminate causes, which is the name of the game here. Even though we were getting no response and it was frustrating, it allowed us to take things off the table. So this is a fishbone diagram. This is a standard way we diagnose anomalies and try to resolve them. The green boxes are things that are possible causes. The orangish boxes are ones that we eliminate. And at the top, you can see we have mission operations issues. Then we have a row that's about fault protection issues. Then we have telecom and TMU issues. And at the bottom are the FDS problems. So you can see we came down on the FDS pretty solidly. And this was our high-level tree. The low-level tree has more steps, but essentially it's the same game. We kept asking questions. This was the MDS interface. This was flight software issues. We had a possible memory corruption. We had processor issues, which we just didn't think were right. The telecom system, we were still keeping on the table a little bit over here. Then we had all of those other boxes kind of along the bottom and onto the left here. And then right in the middle, we have the memory and inverter issues. So we thought we either had a flight software corruption or some sort of a memory issue. So after a very long wait, we finally got to the point where we got an interesting answer from the spacecraft. So I'm going to talk about that next. So without the telemetry, we'd gotten down to the fact we were talking about the FDS memory. And this is actually a picture of the flight spare. We also finally figured out why we couldn't get the telecom system to behave we wanted all the time. It turns out that the CCS can issue commands based with a timestamp, or it can issue commands based on having a frame start. The FDS produces frame starts. So the part of the FDS that was producing the clock data was good, but the FDS was not telling frame starts. So we had a mix of the command types, and we hadn't realized that. It had been so long since it mattered. But anytime we sent something with a frame start, it wouldn't work. Anytime it had a timestamp, it would work great. So once that came together, it told us again, part of the FDS was working, but certainly parts were broken. So how does this software work? David Cummings is one of the heroes of the story. He's a software engineer in JPL, and he reverse engineered the software and mapped out the functionality. So we have 10 different data modes that we used since the start of VIM. The data modes each collect, package, and route data from the FDS to our modulation system. And those can be thought of as programs. What was really going on here in his mind is that we couldn't start or change these programs. And then our data modes sit on top of some code that uses 4 different P tables. P tables are just code groupings, so they're like collections of subroutines. A given data mode might use code from different P tables. So he felt the fact that none of our commands to use the data modes were working implicated the P codes, the P tables. So what we wanted to do is restore just the 4 data modes that are currently in use. We'd started with 10, but we're so far away now, we only use 4 of them, the low rate modes. So our breakthrough was Dave asked a great question. If the code execution was somehow stuck in a P table, how could we unstick it? So we have 2 variables in memory. They determine which data mode we use and hence which P table is executed. Mode and C mode. So mode is what you get if you try to command the FDS from the ground. And that obviously wasn't working. And C mode is set by the code based on the value in mode. So Dave's idea was to use hardware pokes, and we would force the mode and C mode to the correct value for each data mode. Now, we'd never done this in 94 years of flight due to the risk. We have some experience on several missions where these pokes have killed spacecraft. So we want to be very careful, but we didn't have much option here. So we built a set of 20 pokes, and our attempt was to force the code to respond. And this was uplinked on March 1st last year, just about a year ago. And the initial reports were, again, it looked pretty grim. We didn't see much response, and we didn't see telemetry or anything. But the DSN was, again, monitoring this on the recorder. And the pokes definitely appeared to elicit a response. So this is the subcarrier frequency changing, and you can see there's evidence here of modulation in some of the modes. And then these two lines are basically our dial tone, ones and zeros. So we were getting modulation on the signal. Since the FDS did something, it told us a lot. The FDS processor responded to the poke clearly. It told us that portions of memory were still sound and executing code, and the anomaly was likely due to a memory corruption. And the DSN was then able to take this telemetry, and even though they didn't have frame markers, they figured out a way to decode it, which was an amazing bit of work that they put out in about a weekend. And so they gave us these tools to manage this telemetry. And what we got here was a big break. It turned out that the last mode we left it in, somehow Voyager was in a mode where it was dumping its memory from the FDS, which was pretty incredible. So the downlink we were getting was a full memory dump, which is something we absolutely wanted to get, of course. This was completely accidental. We still don't understand how it happened. Just dumb luck. So the further analysis then showed us that we had 256 contiguous words with corruptions. And those are the addresses. And these locations were critical. They all contained subroutines shared by all of the P tables. So it wasn't even the P tables, it was the supporting code underneath those. So about 3 layers deep in the code. By the next day, we traced it down to a single RAM chip. So this is the chip that's responsible for the 5th bit in each address location. So we understood what was going on. And if you're a code nerd and you want to understand what we're looking at, this is a little bit of the assembly code from the FDS. This is 1400 to 14FF for the address. This is the value we expected to see. And you can see in some cases the words are fine, but in other cases where the failed chip was not at the right address, you would see it change. So the code was nonsense. These are the labels. This is the actual assembly command. This is the parameters associated with it in the next column over. And then, of course, some very cryptic, sometimes comments that were put in. So now that we knew what was wrong, we could proceed with a fix, which again is not very easy when you're 15 billion miles away. So we really wanted telemetry data. It had been 4 months. And we also knew that we had very few free memory locations. So our priorities based on that were to demonstrate control of the processor, restore engineering telemetry, and finally get science back, because that's why we would be flying the spacecraft. The key challenge, though, was those memory constraints. Because it was so tight at the beginning of VIM, the code jumped everywhere. It jumped between the actual data mode code to the P tables to these other sections underneath. Constant jumps back and forth to reuse code all over the place. It was spaghetti. Another was the fact that we hadn't done anything for 3 decades with this computer. So we had to kind of reinvent our uplink processes and checks since we hadn't done this in a long time. So the first step is earlier we'd found this piece of code, and we knew there was something called min-cmrot. This was a piece of code that was used when you load software to the FDS. So David disassembled it, reverse engineered the functions, and confirmed that this is actually what this 267 piece of code was. So it became our hello world. And the idea is that if we put this on board, it would give us some clock data with telemetry markers, which would be great. So David and Armin Arslanian, who is the other hero of our story, another flight software person, they morphed this into a readout program, which would return frame memory readouts. Even though we already had them, we wanted to show that we could actually do something with the Hello World program. So we commanded the FDS first to inhibit frame generation, because we have commands that might have been queued up and ready to execute, including FDS commands. We didn't want to re-enable the processor and suddenly get these frame starts and have a bunch of commands tumble out. So we disabled that. We uplinked the min-cmrot on March 8th, and it worked. And on March 15th, we uplinked min-mro, and it worked as well. So this was great news. So we had control of the processor. Now we had to get the engineering telemetry back. So we had 256 instructions that had to be relocated. We had to preserve the behavior and timing of the code. And we had to cannibalize obsolete engineering high rate mode. This was some of the data modes we didn't use anymore. So we knew we had a little code we could play with, but it wasn't clear how much of this was reused in other areas. The challenges here for our flight software people were that we had no reliable instruction set version. We had multiple versions on the ground, but we weren't sure what was actually on board because it hadn't been played with for 35 years. We had no reliable source code version or listing on the ground. We had Microsoft Word version, and it had potential errors because an optical character recognition scan, and it was in a Word document. So we weren't sure it was right. We had no assembler, we had no software simulator, and we had no hardware test bed. So pretty much mission impossible from a programming standpoint. So because we didn't have an assembler, we had to just modify binary instructions. And that, of course, can be problematic. What if we accidentally overwrote something that was used in memory elsewhere? What if we didn't recognize the correct jumps to in and out of relocated code? What if we missed something about the instruction set or the existing code? How do we debug it if we mess it up? Could it get worse? So the solution they came up with to get around all these problems was to use a checklist. They thought of every single mistake they could make, and then they built a checklist of that, and they iterated the new code with multiple people. So this approach was not exactly low risk, but they deemed it as being less risk than the fact that we had no telemetry, and it couldn't get much worse, frankly. So this patch was loaded and linked on April 20th, and we got our first telemetry in 5 months. So in the middle, this is Armin and this is David. So those are two guys that built all the code. This is David back here with his arms up. He was pretty happy. So we still weren't done yet. The team had to use the same process to build another patch, and this was to get our 3 science modes back. We initially thought this was going to be a harder problem. It actually ended up being easier because so much of the code was common and reused. So the new challenges and solutions we have is there still wasn't enough space. We really used most of it up for the engineering fix. So we found an old memo that mentioned that there was some free memory in a certain location. And it looked free in the code, but again, since we didn't really understand this code, we weren't completely certain. It also would have been desirable to use the lower memory. So the memory split into 2 pieces. We were playing primarily in the upper addresses. To go down to lower memory, you have to add steps. You have to add a special jump command. So adding that seemed like it was a bad idea. So we actually found some unprotected areas in higher memory and used those. And again, this was a risk trade. So this patch was uplinked on May 18th, and it worked as well. And we had science telemetry. So I want to point out, I'm highlighting this step. I keep saying the patch was uplinked on a date, and it worked as well. It sounds very trivial, but these were amazing jobs that these two did and the flight team did in terms of actually getting the uplinks on board the spacecraft. This was a pretty heroic Eric. So I feel like when I say that, it kind of takes away from what they did. So let me explain exactly what they did. This is a map of the SDS memory. Across in the x-axis, it's 0 to 255. And then it's the upper memory, so it's address 4,000 up to 8,000. What you're seeing here is the blue line across the middle. This is the line of failed bits. So this was where we lost words. This piece of the memory was basically no good. We had this copy program in the middle, which we didn't need, but we thought we needed everything else on either side of copy. So what Armin and David did is they took all of this code, split it up into 14 pieces, and wrote it wherever you see the orange bits. So you can see it's spaghetti code, and they got it to fit all together, which is pretty cool. To pull that off, they had to make 89 specific changes in the code. And this is this is across to, I can't remember if it's 90 or 100, but it goes up to 0 to 8,000. Armin made these plots, and it shows you every single location where they had to make a change. So 89 total points where they had to modify instructions without an assembler, without a test bed, without simulator. Pretty cool. So we still weren't done. Meanwhile, the flight team had to get our operations back up. So they, number one, restored FDS frame generation so we could command normally. They had to resync our clocks because those had drifted. We have some autonomous things on board we had to worry about, get some of them working, make sure some of them weren't going to surprise us. And then 3 of the instruments had fallen kind of into these anomalous states because the FDS wasn't telling them what to do. And in the worst case, the OECP here, our low energy particle analyzer, this upper piece here is on a table that rotates, and it's got over 8 million cycles on it, and it had not stepped for 5 months. So it was sticky, and it took a while for it to break free. So we were pretty worried we'd lost the stepper motor for a while, but it began to work. So we began nominal operations at the end of May, and then the last two data modes were tested in July. So that's the story of how you fix your computer that's 47-year-old from 15.2 billion miles away. So what do we take away from this? Well, the Voyagers illustrate a fantastic balance of flexibility against understandability and intrinsic robustness. So let me unpack that. It's flexible code at some level, but people can understand it, and it's very robust. As I said, there's no safe mode here. So in my opinion, we've kind of lost our way in spaceflight with very complicated fault protection designs and very complicated processor designs and software designs. I don't know if we'd recover Voyager if this was a more modern mission, in my opinion. The negative is the relative health of the Voyager spacecraft for decades contributed to a loss of knowledge. So in other words, if you never get sick, you don't have a lot of experience going to the doctor. And that was definitely our case. The spacecraft had been so good that we didn't have knowledge about the FDS. We hadn't had to play with it really. Let's see. So the other difficulty we had could have been avoided. We have abandoned or discarded commands, tools, and test beds, some of which I mentioned. We have lost or inaccessible documentation. And then I think there's always been a perception, even back in the 1990s, that the interstellar mission would be short and the data wouldn't be valuable. And it's actually the opposite. It's probably our most valuable data. So having these three factors are things that could have been avoided, but it's just the reality of keeping an extended mission funded at just the minimum level so that it survives. And that's where we've been for 30 years. So we're trying to move forward with these issues. This highlighted things for us, and we want to address our final goals. So this is a chart I'm not going to go into depth on, but it's Voyager 1 at the top, Voyager 2. The years are in the gray boxes. The AUs are in gold. This is AUs from the sun. And what you want to do is see how far you can stretch the instruments. So you can see all of our instruments get turned off over time. These little building blocks in multicolor, these are steps we can take to push this timeline to the right. So every one of these guys that we can implement gives us new life. The problem is out here on the far right of the page, you can see that the relative, the estimated survival probability is very high up until about the 50th anniversary. Then we have to start taking more and more chances. And then out in the 2030s, it's pretty unlikely the spacecraft will live. There's some games we can play, but we just don't think it's going to work. So you never know with Voyager. Sometimes we get really lucky, as you've seen, and get magical memory readouts. So we do have another mission. Susie Dodd is our project manager. She calls them the Voyager's humanities spacecraft. And that's because they really do matter and inspire people. Our media coverage was positive and supportive during this, which is kind of rare these days. We had 90 significant media hits in established outlets. It was a very popular story on our website and was there for over 3 months. It was in the top 3 stories for over a month. And the social media posts were also far above benchmarks. So people really care about Voyager. And for us, it's the best part is getting the great fan mail. And that is it. Thank you for your attention.
Thank you so much, Bruce. Very appropriately on Valentine's Day, we talk about a spacecraft we love so much too. So thank you for coming in. That was an amazing talk. And I'm going to open it up to questions. So if you have some, please put them in the chat. Oh, Dina has put the first question in. So I'll go with that. How does working with such a legacy spacecraft differ from managing more modern missions? And how did the team celebrate after their success? Does it involve famous JPL peanuts? Oh, okay, this is all one big question.
It was Voyager doesn't get a lot of attention. It's not the coolest spacecraft to work on in many ways. So sometimes you don't get the fresh outs or the really brilliant people, but when things go wrong, we did get the brilliant people. So in many cases, it's kind of hard to get people to work on Voyager, but it's actually the best training ground we have because it's such an interesting mission. And in some ways, it's kind of simple. You can learn to make risk trades. They're more accessible, I guess, to people. So I love it as a training ground, and I'm very challenged by it. And I have many, many years of experience. So Voyager is always my favorite mission. We didn't really celebrate per se. We kind of sat around in the conference room and we were really thrilled, but then we had to kind of get back to work and try to get things recovered. So it was a very long celebratory set of months.
I did, as part of me really reacted to your cryptic comments because I've read a lot of student code and some of that is just peppered with cryptic comments like that when you were what you were seeing. But so can you tell me, is it true? So it's the fifth bit that was corrupted throughout that was causing all the problems, or was that
So yeah, for that 1400 to 14FF, those addresses,
yeah.
every word had the fifth bit set to, I think, 1. I can't remember if it was 1 or 0. But effectively what happened was the chip failed and it failed to 1. So if there was supposed to be a 1 in the fifth bit, the address had the right data in it. But if it was supposed to be the alternative, it was the wrong. It was just a nonsensical word then. So the code everywhere the FDS tried to run, it kept reaching into this set of corrupted bits, and that's why the processor wouldn't function right.
Yeah. So I know you sort of have mitigated some of the problems because of that, but have you gone back and tried to figure out why that happened, or is there a
We have multiple. The B memory has every location in memory has a failed bit, and that happened at a higher level. That happened in one of the output units, or no, it was an output unit. So this was actually a specific chip that failed, and so it hit us in a more localized region. We don't know why.
ah,
We're subjected to cosmic rays of enormous energy. It could have been a bit hit. It could have just been a chip that had been kind of marginal and aged after 47 years in space. So we don't have the money
right?
to investigate really, and frankly, nobody would care about our chips at this point. But
Yeah. Are those chips still around?
I have no
Are those
idea. I don't think we have any in our stores. There might be some people who have them sitting around in antique hardware, but certainly none
yeah.
of them are still operating or continuously for that one.
Yeah. So Bob has a question. What differences have evolved between Voyager 1 and Voyager 2?
Um, boy, Voyager 1 is in deeper trouble in terms of thruster life, and um, we have significant differences in power system. That was one of our big surprises this year. I told you we went to an unregulated bus. Voyager 2, we had very good success. We've been able to operate an extra 2 years effectively with an unregulated bus. You notice if you remember earlier this year, we had another anomaly on Voyager 1 where we lost contact and went to the S-band transmitter. That was due to the fact that we assumed that Voyager 1 and 2 had the same power margins out of regulation. And this is based on documentation that we had, but they are behaving very differently. Voyager 1 cannot go very far unregulated before we hit a problem. It undervolted. And that's why we ended up on the backup transmitter. So the power systems are
Yeah, but
behaving very differently. And there's also Voyager 2 tends to be colder than Voyager 1.
ah, nice. So, but are you learning things from Voyager 1 that you can sort of now troubleshoot Voyager 2 better, maybe?
We always are looking for anything we can to leverage. Voyager 2 is in some ways our test bed because it's not as far away. But we're kind of beginning that may change because we had that, remember on the initial science page, there was a jump up in the plasma density. That feature has opened up a lot of debate. We thought we left the Heliopause in 2012, but one person had a theory that they didn't, which was not really acknowledged, and he made the prediction we would see that bump up. So suddenly the team is going, well, did we enter interstellar space? And there's a lot of debate suddenly, which sounds ridiculous. Our scientists don't know where they are, but that's the point of us going there is nobody knew what to expect. And now we're getting some competing theories based on the data. So it's really exciting, fresh science that it matters and it's so relevant. And this is from a mission that's 50 years old.
Yeah. Of Glenn, actually, the segues nicely into Glenn's question, which is, can Voyager still take images? And is there any science to be gained from that at this point?
No, our instruments they're Vidicons. They're basically 1960 Vidicons units, and they take a lot of power, so we don't have the power to turn them on. And if we did,
Yeah.
those systems don't have the adequate resolution compared to CCDs and things that they could do anything useful. But we're so power starved. I mean, we're scraping the barrel for anything we can do to turn off and not freeze. So that's we're having to turn off we're having a downtime in our big station at Canberra that does uplink. So we're actually going to be turning off two of the particle instruments to get through that a little bit early because we just won't have an antenna.
Wow. So you talked about how if you thought that if this was a modern mission, you might have lost the spacecraft. Like this, a lot of this was possible because there's kind of so much knowledge about Voyager. But what have you learned from this that you guys are taking forward into JPL, how JPL designs, and you know what kind of lessons are you taking forward to your more modern missions?
Well, we have one of our original designers is present on our team, and that's his quote effectively. Excuse me. His quote is about, you know, the simplicity of the Voyager code, and the robustness is balanced pretty perfectly against the flexibility. And much of our code these days is a little too flexible in my bit. Sometimes we don't understand what the fault protection is going to do. Even if you have simulators and things, they behave differently. So I don't know if anybody's going to learn because often we don't learn from lessons, right? But that's the lesson that we certainly took away from this anomaly was that we had such a nice balance of flexibility against robustness, especially. It was miraculous we got the spacecraft back. I think many of us were pretty doubtful. So I hope some of the people that build code and processors at JPL take note and think a little more deeply about what they're doing. But it's across the industry.
Yeah,
It's not just JPL. It's just we have these very powerful processors and we have a lot of room to write code. And people say, "Oh, I'm going to make it perfect," but maybe
yeah.
that's sometimes the enemy of good enough.
Yeah. Yeah. I mean, I know that you were talking about that full memory dump that sort of inexplicably happened. And have you since done any kind of gone back and done any kind of sort of post-mortem to see, was that how did that was that built into the code? Was there a sort of a was that a feature, a bug? Like how did that happen?
Well, yeah, we still don't understand it. I don't think we will, and we probably don't have the resources. The person I mentioned, Bob Rasmussen, who's one of the original designers, he thinks that it's just kind of a feature of the way it works. It tends to plug into a telemetry stream as it's sampling through, and just by dumb luck, when it went through one of these odd modes, it ended up in a position where it was listening to the FDS, and somehow the FDS was in a memory readout mode. So we really don't have a good explanation for it, and I don't think we necessarily ever could because unless we took that bad code and like ran endless simulations. So
Yeah.
and it would be hard to replicate because we don't know exactly when the chip failed and how the code went, and it's crazy.
I'm sure you have some hapless PhD student who would love to take this on as a
I
project.
don't know.
Because August asks, is the golden record still on Voyager?
Absolutely. It'll be there forever. So the spacecraft will
Yeah.
probably lose around 2030. And as I said, they'll be orbiting the galactic center for potentially billions of years. And that record should be good for a few billion years. So they will drift nearby stars, meaning probably like hundreds of AU close to a nearby star, but they're effectively just going to drift in the around the galactic center for eons. And the record may
Wonderful.
degrade, but the spacecraft will still be there. So,
Yeah. Glenn says, are lessons learned from the Voyagers being applied to New Horizons?
um, they're pretty different spacecraft. New Horizons is a very modern spacecraft in comparison. They actually are still using their cameras here and there to do observations of bodies, Kuiper bodies, and even I think they were doing Uranus and Neptune science. So they've been actually able to use their cameras, but they are also getting to the point where they're going to have to start managing their power more carefully. So we talk to them occasionally, and they're probably going to be following our footsteps in terms of trying to think of really creative ways to turn things off and not lose the mission.
So Aditi says, how do you address transfer of information as the original designers retire or leave? Are they brought back?
In some cases, we get very lucky. People have other jobs, and when they retire, it's often easier to kind of snag them and bring them back to Voyager, because it's a fun mission to work on, right? And if they have
Yeah.
any history with it, they'll come back. Otherwise, we try to document things as best we can. And we do have all the information, as you saw. It's just that it can be very hard to extract it and explain the different versions.
Yeah. Some more questions in the chat, sorry. What was the risk analysis based on environmental, such as deep space temperatures, and how can this be a lesson learned for future missions?
The analysis was really good. The initial analysis in the 70s. I'm sure everybody's aware of watching Voyager movies and documentaries that the original mission was just to explore Jupiter and Saturn. And the engineers built in Uranus and Neptune. They put in extra capability, and some people actually thought about reaching interstellar space. Of course, nobody knew where the Heliopause would be, and we still don't know, perhaps. But people built this spacecraft to last a long, long time, and it has. And it's interesting that many of the margins we're bumping up to seem to be all kind of like lining up around this 50-year anniversary. It seems like somebody just kind of was looking at the system overall, and maybe it's just dumb luck or coincidence, but it's eerie sometimes how the end date for all of these subsystems is happening at this nearly the same year after all this time. So I think people were consciously thinking about making these spacecraft last as long as possible and making them robust. So it's pretty cool.
Yeah. So there's just time for one final question, and this is from GR Faith. She says, who says, is it possible to point Voyager such that it will eventually drift closer to a star tens or hundreds of millennia from now? Because you did say that there was about 44 years of fuel left. Is that, or you're at the half-life of plutonium?
Yeah, so we have about power till 2030. That's the point where we'll go where our bus undervolts, and that ends the mission. So we were asked this question, could we target the Voyagers to fly to another star system? And number one, we don't have much fuel left. We have about 10% of our fuel left on both spacecraft. So we couldn't do much. And the other problem is that I'm not sure we understand the proper motion of stars orbiting the galaxy. So we might target it, but we don't really know that motion well enough that I think we could target something to make any real difference. And of course, it's a multi-body problem. You have all these different stars tugging on Voyager. So it would be a pretty nasty calculation. So when we were asked the problem, we said it was better to collect the interstellar data for, an extra 5 or 10 years versus trying to burn up all your fuel and lose the mission for something that we would never get data back and probably wouldn't make a difference in terms of someone finding the spacecraft.
Yeah. Thank you so much, Bruce. I
Question.
cannot thank you enough. Thanks for this wonderful talk. You get all the claps and snaps today. And now I think Dina can tell us what we're doing next.
Next up, we've got Shayla Redmond, who is already in the audience here. She is going to be talking about space communication as a NASA ambassador, and we'll be heading to Shayla's talk in about 7 minutes.
Well, thank you, everyone.
Thank you so much, Bruce.
Yeah, thanks, Bruce. Thanks everybody for joining us for a really great nerdy start to the 9th Roger That. We'll check back in 7 minutes then. Hi, Shayla.